invention is a new invention.
What if our universe comes with a self-destruct button to eliminate itself so cleanly and efficiently that every single physical thing would just stop existing and life would be impossible forever? The ultimate ecological catastrophe. Vacuum decay. To explain how our universe could destroy itself, we need to understand two principles. 1. Energy levels. A core idea in physics is that everything has an energy level. The higher the level, the more energy is in the system. Wood, for example, has a high level. It can be burned, a process that releases the chemical energy stored in its molecular bonds and turns it into heat. The ash left over is at a lower energy level than the wood before. 2. Stability. Everything in our universe tries to move towards its ground state, in which it's completely stable and has as little energy as possible. For example, a ball on a hill is unstable and has a lot of potential energy. When disturbed, it will roll down into the valley and lose its potential energy in the process. The ball is now in its ground state and stable. It will remain like that. Everything in our universe follows these two principles. If something has a lot of energy, it's unstable and wants to get rid of it to become stable and reach its ground state. This is true for every system, even in the weird world of quantum mechanics. If our current understanding of physics is correct, then the universe gets its properties from quantum fields. We explain them in detail in another video. For this video, imagine them as the rules of the universe. They tell particles how to behave and interact. Like everything in the universe, they want to be in the lowest energy level possible, which is called a vacuum state. This has nothing to do with vacuum in space. It's just called this way because scientists are bad at naming things. We think all the fields reached their vacuum state, except maybe one. It's possible that the Higgs field is not stable, but metastable, which is a fancy way of saying that it pretends to be stable, but really is not. It would be a false vacuum. The Higgs field is responsible for giving particles their mass, which rules how almost everything in the universe interacts. What would happen if the Higgs field is in a false vacuum? Think of our ball in the valley. The ball is the Higgs field. The valley might not be the lowest energy state for the Higgs field. There might be an even deeper valley that it wants to get to. This would mean that the Higgs field has a lot of potential energy waiting to be released. The Higgs field could be like a piece of wood, but drenched in gasoline, waiting to set the universe on fire. A random spark, like quantum tunneling, could release the potential energy of the Higgs field. This could happen at any time and without warning. If at any point in space this so-called vacuum decay starts, there is no turning back. As the Higgs field crashes into the lower energy state, it releases a massive amount of potential energy. This energy pushes the space around it over the barrier, which releases more potential energy. A sphere of the new stable Higgs field, or true vacuum, grows at the speed of light in all directions. Imagine it like setting a sea of gasoline, the size of the universe, on fire. The sphere is surrounded by a shell of energy that devours everything it comes into contact with. Whatever it touches is eliminated from existence. The bubble will continue to grow forever, deleting the universe on its way. There is no way to be warned since it's so fast, but there's nothing we can do anyway. Our destruction would be instant. In a fraction of a second, Earth would be gone. But it actually gets worse. If the energy level of the Higgs field changes, it changes all of physics. In the true vacuum of the sphere, the standard model will be overthrown, superseded by different physics that we don't know. How fundamental particles behave, how atoms hold together, how chemicals react. Vacuum decay won't just destroy life, it will destroy chemistry itself, making life as we know it impossible. We simply have no idea what it will be like inside. It might be a shadow of what it is now. Or not. We don't know. If vacuum decay happens, the outlook is indeed grim. If you feel slightly worried now, don't be. At this point, false vacuum is speculation based on our current understanding of particle physics, which might be wrong. It's kind of like using a ruler to measure a continent. sure you can do it, but you might be off by quite a bit at the end. Right now, no one can say if vacuum decay is a thing that's real or just a scary idea. But even if one or multiple spheres of death have already started expanding, the universe is so big that they might not reach us for billions of years. If they're far enough away, they might not ever be able to reach us because of the expansion of the universe. The speed of light is not that fast on the scale of the universe. So while vacuum decay is fascinatingly scary, right now there are other things we should be more afraid of. In contrast to vacuum decay, we have the power to prepare for most of them. The fundamental currency of our universe is energy. It lights our homes, grows our food, powers our computers. We can get it lots of ways: burning fossil fuels, splitting atoms, or sunlight striking photovoltaics. But there's a downside to everything. Fossil fuels are extremely toxic, nuclear waste is, well, nuclear waste, and there are not enough batteries to store sunlight for cloudy days yet. And yet, the sun seems to have virtually limitless free energy. Is there a way we could build a sun on Earth? Can we bottle a star? The sun shines because of nuclear fusion. In a nutshell, fusion is a thermonuclear process, meaning that the ingredients have to be incredibly hot, so hot that the atoms are stripped of their electrons, making a plasma where nuclei and electrons bounce around freely. Since nuclei are all positively charged, they repel each other. In order to overcome this repulsion, the particles have to be going very, very fast. In this context, very fast means very hot. Millions of degrees. Stars cheat to reach these temperatures. They are so massive that the pressure in their cores generates the heat to squeeze the nuclei together until they merge and fuse, creating heavier nuclei and releasing energy in the process. It is this energy release that scientists hope to harness in a new generation of power plant, the fusion reactor. On Earth, it's not feasible to use this brute force method to create fusion, so if we wanted to build a reactor that generates energy from fusion, we have to get clever. To date, scientists have invented two ways of making plasmas hot enough to fuse. The first type of reactor uses a magnetic field to squeeze a plasma in a donut-shaped chamber where the reactions take place. These magnetic confinement reactors, such as the ITER reactor in France, use superconducting electromagnets cooled with liquid helium to within a few degrees of absolute zero, meaning they host some of the biggest temperature gradients in the known universe. The second type, called inertial confinement, uses pulses from superpowered lasers to heat the surface of a pellet of fuel, imploding it, briefly making the fuel hot and dense enough to fuse. In fact, one of the most powerful lasers in the world is used for fusion experiments at the National Ignition Facility in the US. These experiments and others like them around the world are today just experiments. Scientists are still developing the technology. And although they can achieve fusion, right now it costs more energy to do the experiment than they produce in fusion. The technology has a long way to go before it's commercially viable. And maybe it never will be. It might just be impossible to make a viable fusion reactor on Earth. But if it gets there, it will be so efficient that a single glass of seawater could be used to produce as much energy as burning a barrel of oil, with no waste to speak of. This is because fusion reactors would use hydrogen or helium as fuel, and seawater is loaded with hydrogen. But not just any hydrogen will do. Specific isotopes with extra neutrons, called deuterium and tritium, are needed to make the right reactions. Deuterium is stable and can be found in abundance in seawater, though tritium is a bit trickier. It's radioactive, and there may only be 20 kilograms of it in the world, mostly in nuclear warheads, which makes it incredibly expensive. So we may need another fusion buddy for deuterium instead of tritium. helium-3, an isotope of helium, might be a great substitute. Unfortunately, it's also incredibly rare on Earth. But here, the moon might have the answer. Over billions of years, the solar wind may have built up huge deposits of helium-3 on the moon. Instead of making helium-3, we can mine it. If we could sift the lunar dust for helium, we'd have enough fuel to power the entire world for thousands of years. One more argument for establishing a moon base, if you weren't convinced already. Okay, maybe you think building a mini sun still sounds kind of dangerous. But they'd actually be much safer than most other types of power plant. A fusion reactor is not like a nuclear plant, which can melt down catastrophically. If the confinement failed, then the plasma would expand and cool, and the reaction would stop. Put simply, it's not a bomb. The release of radioactive fuel like tritium could pose a threat to the environment. Tritium could bond with oxygen, making radioactive water, which could be dangerous as it seeps into the environment. Fortunately, there's no more than a few grams of tritium in use at a given time, so a leak would be quickly diluted. So we've just told you that there's nearly unlimited energy to be had at no expense to the environment in something as simple as water. So, what's the catch? Cost. We simply don't know if fusion power will ever be commercially viable. Even if they work, they might be too expensive to ever build. The main drawback is that it's unproven technology. It's a $10 billion gamble, and that money might be better spent on other clean energy that's already proven itself. Maybe we should cut our losses. Or maybe, when the payoff is unlimited clean energy for everyone, it might be worth the risk. For most of our history, human technology consisted of our brains, fire, and sharp sticks. While fire and sharp sticks became power plants and nuclear weapons, the biggest upgrade has happened to our brains. Since the 1960s, the power of our brain machines has kept growing exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. Computer parts are approaching the size of an atom. To understand why this is a problem, we have to clear up some basics. A computer is made up of very simple components doing very simple things, representing data, the means of processing it, and control mechanisms. Computer chips contain modules, which contain logic gates, which contain transistors. A transistor is the simplest form of a data processor in computers, basically a switch that can either block or open the way for information coming through. This information is made up of bits, which can be set to either 0 or 1. Combinations of several bits are used to represent more complex information. Transistors are combined to create logic gates, which still do very simple stuff. For example, an AND gate sends an output of 1 if all of its inputs are 1, and an output of 0 otherwise. Combinations of logic gates finally form meaningful modules, say for adding two numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all basic operations are literally simpler than first-grade math, you can imagine a computer as a group of 7-year-olds answering really basic math questions. A large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 14 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable ways we're used to, and traditional computers just stop making sense. We are approaching a real physical barrier for our technological progress. To solve this problem, scientists are trying to use these unusual quantum properties to their advantage by building quantum computers. In normal computers, bits are the smallest units of information. Quantum computers use qubits, which can also be set to one of two values. A qubit can be any two-level quantum system, such as a spin in a magnetic field or a single photon. 0 and 1 are this system's possible states, like the photon's horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of those, it can be in any proportions of both states at once. This is called superposition. But as soon as you test its value, say by sending the photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it's unobserved, the qubit is in a superposition of probabilities for 0 and 1, and you can't predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a game changer. 4 classical bits can be in one of 2 to the power of 4 different configurations at a time. That's 16 possible combinations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. 20 of them can already store 1,000,000 values in parallel. A really weird and unintuitive property qubits can have is entanglement, a close connection that makes each of the qubits react to a change in the other state instantaneously, no matter how far they are apart. This means that when measuring just one entangled qubit, you can directly deduce properties of its partners without having to look. Qubit manipulation is a mind-bender as well. A normal logic gate gets a simple set of inputs and produces one definite output. A quantum gate manipulates an input of superpositions, rotates probabilities, and produces another superposition as its output. So a quantum computer sets up some qubits, applies quantum gates to entangle them and manipulate probabilities, and finally measures the outcome, collapsing superpositions to an actual sequence of zeros and ones. What this means is that you get the entire lot of calculations that are possible with your setup all done at the same time. Ultimately, you can only measure one of the results, and it will only probably be the one you want, so you may have to double check and try again. But by cleverly exploiting superposition and entanglement, this can be exponentially more efficient than would ever be possible on a normal computer. So while quantum computers will probably not replace our home computers, in some areas they are vastly superior. One of them is database searching. To find something in a database, a normal computer may have to test every single one of its entries. Quantum algorithms need only the square root of that time, which for large databases is a huge difference. The most famous use of quantum computers is ruining IT security. Right now, your browsing, email and banking data is being kept secure by an encryption system in which you give everyone a public key to encode messages only you can decode. The problem is that this public key can actually be used to calculate your secret private key. Luckily, doing the necessary math on any normal computer would literally take years of trial and error. But a quantum computer with exponential speedup could do it in a breeze. Another really exciting new use is simulations. Simulations of the quantum world are very intense on resources, and even for bigger structures such as molecules, they often lack accuracy. So why not simulate quantum physics with actual quantum physics? Quantum simulations could provide new insights on proteins that might revolutionize medicine. Right now, we don't know if quantum computers will be just a very specialized tool or a big revolution for humanity. We have no idea where the limits of technology are, and there's only one way to find out. The simple questions are the hardest ones to answer. What is a thing? Why do things happen? And why do they happen the way they do? Let's try to approach this step by step. What are you made of? You are matter, which is made of molecules, which are made of atoms, and those are made of elementary particles. But if elementary particles are the smallest things that exist, what are they made of? To answer a simple question, let's start simply. Let's wipe the universe clean, away with matter, antimatter, radiation, particles, anything. Now let's take a closer look at absolutely nothing. What is empty space? Is it what we call a vacuum? There are no atoms, no matter, nothing. Is it really all that empty? Nothing gives us the building blocks for everything. In a sense, empty space is a lot like a vast, calm ocean. While the water is very still when nothing is happening, a stiff breeze can create some serious waves. Our universe works a lot like this. There are these oceans everywhere. Physicists call them fields. This might be strange and new, but think about radiation, for example. By exciting what's known as the electromagnetic field, a little kink is created, which is the particle we call the photon, the particle that carries radiation. We perceive it as light. This isn't unique to light. Every particle in the universe is made this way. There are fields for every particle of matter, all with their own rules. For example, along with the electromagnetic field, there is an electron field everywhere in the universe, and little kinks in that field are electrons. Altogether, the fields of our universe can produce 17 particles, which can be divided into 3 categories: the leptons, and the quarks, and the bosons. Leptons consist of the electron as well as its cousins muon and tau particles. Each has an associated neutrino. Then there are quarks. The quarks are the nuclear family of particles. They're always found bound together in groups and pairs and make up protons and neutrons, which make up the nuclei of atoms. Together, the leptons and quarks are the matter particles. They make up all the things you see: the air you breathe, the sun that warms you, the computer you're using right now to distract yourself from the stuff you should be doing. But things don't just exist, they also do stuff. In some philosophical sense, the properties of a thing are just as much a part of it as existence itself. This is where the bosons and the fields that make them come into play. While the quarks and leptons are made by matter fields, the bosons are made by force fields. We call a rule of the universe a force, and so far 4 fundamental forces have been discovered: electromagnetism, gravity, and the strong and weak nuclear forces. These forces are the rulebook of a game where the pieces are particles and the game is the universe. They tell particles what they can do and how they can do it. Bishops move diagonally, massless particles move at the speed of light, knights can jump, gravity attracts. The forces are the rules for how particles interact, which ultimately make them the rules for how particles assemble into all the big things we see in the universe. Gravity isn't just the rule for orbits around the sun or apples falling from trees. As a rule, it says matter attracts, which builds planets and stars. Electromagnetism isn't just a rule for magnets attracting or repelling, or electric currents in light bulbs. It governs all atomic bonds, building every molecule. Together, forces and particles are sort of like the tinker toys of existence. The bosons are like messengers, passed between, you could say, connecting the matter particles, which they use to tell each other how to move. Each particle uses a certain set of the forces to interact with other particles. Quarks, for example, can interact with each other with electromagnetism and the strong nuclear force, but electrons don't use the strong force, just electromagnetism. The quarks exchange strong force bosons, communicating the strong nuclear attraction to each other, while the protons they build exchange particles of electromagnetism, photons, with the electrons. Thus, the quarks end up locked up in nuclei, while the electrons remain attached by their electric attraction, building atoms. Even though the universe has lots of big, messy phenomena like life, supernova, and computers that seem complex on the surface, if you zoom in far enough on anything, you just get 17 particles emerging from underlying fields, playing a game with 4 rules. To summarize, in the most basic form we know right now, this is what things are. This theory is what physicists call the standard model of particle physics. You are basically nothing more than disturbances on an ocean that's excited by energy and guided by forces that make up the rules of the universe. But why? And what is a force? We'll have to explore a few more simple questions to get to the bottom of this. Humans have existed for millions of years as part of nature. But then something changed, and in an incredibly short amount of time, we terraformed this planet and designed it to fit our needs. As far as we know, we're the first beings to awaken and completely take over a planet. the transition from hunting and gathering to farming and building was so breathtakingly fast that many of our ways of thinking about the world are no longer useful. One of our most outdated ideas is that the most commonly used calendar in the world insists that we live in the year 2016. This distorts our view of our own history and makes it harder to understand who we are as a species, and just how far we've come in an incredibly short amount of time. So maybe it's time to choose a year zero for humanity. A year zero that truly represents us as a species and includes all cultures. A year zero that marks when we began building our own world on top of the old one.
But
12,000 years ago, hundreds of humans came together in the hills of southern Anatolia. They were hunters and gatherers without knowledge of agriculture or metalworking. All they had were tools made of stone and wood. But they built humanity's first big construction project, 7,000 years before the pyramids were built in Egypt. Spread over 300 meters, our ancestors erected circles of massive stone pillars, each of them up to 6 meters high and 40 tons in weight. Decorated with artful pictograms and stone carvings of animals and mythical creatures. We have no idea how they were able to do this. It was probably a project of epic scale for the Stone Age, requiring a level of organization we didn't know early humans were capable of until we found this site. So, why did they build it? The most popular theory is that this was the first temple of humanity, dedicated to long-forgotten gods. We only know that this construction project, the first of its kind, marks the beginning of a new era. It's in this area, around that time, that humans truly began to build their own world, which would make it a fitting milestone in our history for the start of our calendar. This moment in time is so distinct that scientist Cesare Emiliani proposed that humanity should switch to what he called the Holocene calendar by adding 10,000 years to our current Gregorian calendar. We don't need to change our well-established days and months, and religious calendars could stay the same as well. But for all official purposes, our current year would be the year 12,016 of the human era. This would drastically alter how we think about history and how it feels. Let's take a very brief look and move through our new history from our new year zero. 12,000 years ago saw the beginning of the first construction project, kicking off our history. It would be in use for about 2,000 years. It took nearly a millennium until Jericho, probably the first city on Earth, was founded in the year 1000 after the start of the human era. Progress was still very, very slow at this point. Over the next 1,000 years, more and more permanent settlements appeared around the world, and more plants and animals were domesticated as agriculture spread. Evidence for trade over thousands of kilometers has been found from this period. Around 5 million humans were alive at this point in history, fewer than live in London today. Technology advanced constantly at a slow pace. Pottery became widespread. The first cultural communities appeared in China, India, and the Fertile Crescent. Around the year 4000, 8,000 years ago from today, humans started to use metal for the first time, learning to mix tin and copper and kickstarting what we know as the Bronze Age around the year 5000. The first proto-writing emerged and the wheel was invented. In South America, the Chinchorro culture started to artificially mummify humans 2,000 years earlier than in ancient Egypt. The first high cultures began emerging around the year 7000. The Indus Valley Civilization, ancient Egypt, the Minoans in Greece, and the Sumerians in Mesopotamia. Stonehenge was built in Britain, and the first dynasty in China began. Ötzi the Iceman lived around this time. What we consider history now started, and things began picking up pace as the world population rose to over 30 million. A number of new high cultures appeared around the world, many writing down their legends. More and more cities were founded. In South America, the Olmec culture emerged. Around this time, the legendary Siege of Troy is supposed to have happened. Soon after, in the eastern Mediterranean and the Fertile Crescent, the Bronze Age ended in violence. Every Bronze Age culture, except Egypt, was destroyed by mysterious invaders. Writing and progress froze for hundreds of years. Around the year 9500, what we consider Western culture began. The Greek city-states beat off the Persian invasion and triggered their golden era, ended by Alexander the Great around 9700. 100 years later, Rome destroyed Carthage and became a dominant force in the world. Caesar was murdered in the year 9956, while the world population had risen to about 300 million people. And it's only now, around the year 10,000, that we've reached the point where the Gregorian calendar and our current method of marking human history begins. A mere 2,000 years from now, humans will walk on the moon. If we think about history as we do now, we are underplaying 10,000 years of human progress and development. Including all of it in our calendar makes our past more impressive. It shows how progress became exponential with time, and it incorporates all humans from all cultures into our calendar. A new year zero for our history could reframe how we think of ourselves. As a building project that started 12,000 years ago, when for the first time our ancestors came together to carve a temple out of bedrock with tools made of stone, not knowing what they would set in motion, where it would lead us as a species. From building the first temple to ships flying beyond the sky. Is there a border we will never cross? Are there places we will never reach, no matter how hard we try? Turns out there are. Even with science fiction technology, we are trapped in our pocket of the universe. How can that be? And how far can we go? We live in a quiet arm of the Milky Way, a spiral galaxy of average size, about 100,000 light-years across, consisting of billions of stars, gas clouds, dark matter, black holes, neutron stars, and planets, with a supermassive black hole in the galactic center. From afar, our galaxy seems dense, but in reality, it consists mostly of empty space. With our current technology, sending a human to the closest star would take thousands of years. So our galaxy is pretty big. The Milky Way is not alone though. Along with the Andromeda Galaxy and more than 50 dwarf galaxies, it's part of the Local Group, a region of space about 10 million light-years in diameter. It is one of hundreds of galaxy groups in the Laniakea supercluster, which itself is only one of millions of superclusters that make up the observable universe. Now, let's assume for a moment that we have a glorious future. Humanity becomes a Type 3 civilization, does not get wiped out by aliens, and develops interstellar travel based on our current understanding of physics. In this best-case scenario, how far could we possibly go? Well, the Local Group. It is the biggest structure that humanity will ever be a part of. While it is certainly huge, the Local Group accounts for only 0.00000000001% of the observable universe. Let this number sink in for a moment. We are limited to 100 billionth of a percent of the observable universe. The simple fact that there is actually a limit for us and that there is so much universe that we will never be able to touch is kind of frightening. Why can't we go further? Well, it all has to do with the nature of nothing. Nothing, or empty space, isn't empty, but has energy intrinsic to itself, so-called quantum fluctuations. On the smallest scale, there is constant action, particles and antiparticles appearing and annihilating themselves. You can imagine this quantum vacuum as a bubbling pot, with denser and less dense regions. Now, let's go back 13.8 billion years when the fabric of space consisted of nothing at all. Right after the Big Bang, in an event known as cosmic inflation, the observable universe expanded from the size of a marble to trillions of kilometers in fractions of a second. This sudden stretching of the universe was so fast and extreme that all those quantum fluctuations were stretched as well, and subatomic distances became galactic distances, with dense and less dense regions. After inflation, gravity began to pull everything back together. At the largest scale, the expansion was too quick and powerful to overcome, but at smaller scales, gravity emerged victorious. So over time, the denser regions or pockets of the universe grew into groups of galaxies like the one we live in today. Only stuff inside our pocket, the local group, is bound to us gravitationally. But wait, what's the problem then? Why can't we travel from our pocket to the next one? Here, dark energy makes everything complicated. About 6 billion years ago, dark energy took over. It's basically an invisible force or effect that causes and speeds up the expansion of the universe. We don't know why or what dark energy is, but we can observe its effect clearly. In the early universe, there were larger cold spots around the local group that grew into large clusters with thousands of galaxies. We are surrounded by a lot of stuff. But none of those structures and galaxies outside of the local group are gravitationally bound to us. So the more the universe expands, the larger the distance between us and other gravitational pockets becomes. Over time, dark energy will push the rest of the universe away from us, causing all the other clusters, galaxies and groups to eventually become unreachable. The next galaxy group is already millions of light years away, but all of them are moving away from us at speeds we can't ever hope to match. We could leave the local group and fly through intergalactic space into the darkness, but we would never arrive anywhere. While we will become more and more stranded, the local group will become more tightly bound and merge together to form one giant elliptical galaxy with the unoriginal name Milkdromeda in a few billion years. But it becomes even more depressing. At some point, the galaxies outside the local group will be so far away that they will be too faint to detect, and the few photons that do make it to us will be shifted to such long wavelengths that they'll be undetectable. Once this happens, no information outside of the local group will be able to reach us. The universe will recede from view. It will appear to be dark and empty in all directions forever. A being born in the far future in Milkdromeda will think there is nothing but its own galaxy in the entire universe. When they look far into empty space, they will only see more emptiness and darkness. They won't be able to see cosmic background radiation, and they won't be able to learn about the Big Bang. They will have no way of knowing what we know today, the nature of the expanding universe, when it began, and how it will end. They will think the universe is static and eternal. Milkdromeda will be an island in the darkness, slowly getting darker and darker. Still, with its trillion stars, the local group is certainly large enough for humanity. After all, we still haven't figured out how to leave our solar system, and we have billions of years to explore our galaxy. We have the incredible luck to exist at the perfect moment in time to see not only our future, but also our most distant past. As isolated and remote as the local group is, we can perceive the entire universe, grand and spectacular, as it is right now. Life is fundamentally different from dead stuff, or is it? Physicist Erwin Schrödinger defined life this way. Living things avoid decay into disorder and equilibrium. What does this mean? Let's pretend that your download folder is the universe. It started orderly and got more and more chaotic over time. By investing energy, you can create order and clean it up. This is what living things do. But what is life? Every living thing on this planet is made of cells. Basically, a cell is a protein-based robot too small to feel or experience anything. It has the properties we just assigned to life. It has a wall that separates it from the surroundings, creating order. It regulates itself and maintains a constant state. It eats stuff to stay alive. It grows and develops. It reacts to the environment, and it's subject to evolution, and it makes more of itself. But of all the stuff that makes up a cell, no part is alive. Stuff reacts chemically with other stuff, forming reactions that start other reactions, which start other reactions. In a single cell every second, several million chemical reactions take place, forming a complex orchestra. A cell can build several thousand types of protein, some very simple, some complex micromachines. Imagine driving a car at 100 kilometers an hour while constantly rebuilding every single part of it with stuff you collect from the street. That is what cells do. But no part of the cell is alive. Everything is dead matter moved by the laws of the universe. So is life the aggregate of all these reaction processes that are taking place? Eventually, every living thing will die. The goal of the whole process is to prevent this by producing new entities. And by this, we mean DNA. Life is, in a way, just a lot of stuff that carries genetic information around. Every living thing is subject to evolution, and the DNA that develops the best living thing around it will stay in the game. So, is DNA life then? If you take DNA out of its hull, it certainly is a very complex molecule, but it can't do anything by itself. This is where viruses make everything more complicated. They are basically strings of RNA or DNA in a small hull and need cells to do something. We're not sure if they count as living or dead. And still, there are 225 million cubic meters of viruses on Earth. They don't seem to care what we think of them. There are even viruses that invade dead cells and reanimate them so they can be a host for them, which blurs the line even more. Or mitochondria. They are the power plants of most complex cells and were previously free-living bacteria that entered a partnership with bigger cells. They still have their own DNA and can multiply on their own, but they are not alive anymore. They are dead. So they traded their own life for the survival of their DNA, which means living things can evolve into dead things as long as it's beneficial to their genetic code. So maybe life is information that manages to ensure its continued existence. But what about AI, artificial intelligence? By our most common definitions, we are very close to creating artificial life in computers. It's just a question of time before the technology we build gets there. And this is not science fiction either. There are a lot of smart people actively working on this. You could already argue that computer viruses are alive. Okay, so what is life then? Things? Processes? DNA? Information? This got confusing very fast. One thing is for sure, the idea that life is fundamentally different from non-living things because they contain some non-physical element or are governed by different principles than inanimate objects turns out to be wrong. Before Charles Darwin, humans drew a line between themselves and the rest of living things. There was something magical about us that made us special. Once we had to accept we are, like every living being, a product of evolution, we drew a different line. But the more we learn about what computers can do and how life works, the closer we get to creating the first machine that fits our description of life, the more our image of ourselves is in danger again. And this will happen sooner or later. And here's another question for you. If everything in the universe is made of the same stuff, does this mean everything in the universe is dead, or that everything in the universe is alive? That it's just a question of complexity? Does this mean we can never die because we were never alive in the first place? Is life and death an irrelevant question, and we haven't noticed it yet? Is it possible we are much more part of the universe around us than we thought? Don't look at us. We don't have any answers for you, just questions for you to think about. After all, it's thinking about questions like this that makes us feel alive and gives us some comfort. Are you alone in the universe? Or are you connected to anything? First of all, you're part of a group of mammals that's still very young, but we can make YouTube videos already and build large hadron colliders. We've also split the atom and invented Pokemon. We stem from an ancient life form that began living about 3.5 billion years ago. We feel like we're in control of this planet, but we aren't really. One little asteroid or one creative virus is really all it would take to kill us off for good. Humanity credits itself with being able to destroy the planet, but even with all our nuclear toys, we would probably just cause a huge mass extinction at best. Maybe we could kill 90% of everything living on this planet. Big deal. A few million years later, life would be back everywhere. Most microscopic life and life below the surface wouldn't even be disturbed that much probably. On a geological timescale, our impact on Earth is kind of laughable. We're actually not that powerful. We live on this tiny wet rock that speeds through space following a massive ball of burning plasma. One day, this ball of plasma will stop burning and most likely kill us in the process. If we survive the death of the sun and colonize the galaxy, theoretically, we could survive until the last star in the universe goes out. After that, life becomes pretty impossible. Okay, so everything has an end. Where does this leave you as an individual? At one point in your life, for about half an hour, you were only one single cell inside your mother's womb, a creature just 0.1 millimeters in diameter. Today, you consist of about 50 trillion cells. 50 trillion incredibly complex little biological machines that are much bigger and more complex than the average bacteria. They operate by the laws of physics and chemistry and use micro-machines to build proteins, make energy usable, devour food, transport resources, transmit information, or reproduce. They communicate, duplicate, commit suicide, fight off intruders, and fulfill super specialized duties for the greater good of keeping you alive, so you can have babies. But where is the you part in this if you're made of trillions of little things? The basic information for you is stored in the DNA, a molecule that encodes the genetic instructions used in the development and functioning of all known living things. If you were to unravel it, it would be 2 meters long. If you combined all the little DNA strings in all your cells, you'd get a string so long that it would stretch to Pluto and back to Earth. That's pretty long. And your DNA is a direct connection to your very first ancestor. Take a second to think about this. In every cell of your body, there's a little string of stuff that's been there in various forms for 3.4 billion years. It evolved, it mutated, it duplicated trillions of times, but it directly connects you to the first living being on this planet. We could say you touched every living being that came before you with your DNA.